coming to seminar again. Oh, wait, can you turn off the sound on your computer? Okay, now we won't have any weird echoes. So thank you all for coming. Today we have Ian Roederer, who is from NC State. You are going to, okay, wow, hold on. Too many things went through my brain at the same time. Okay, so Ian did his PhD at that school down the road, and I'm not allowed, I don't know if I'm allowed to say their name or not, as we now actually have a football game against them this semester. But yes, so I'll say it anyway, Texas, that other one. So he did his PhD at Texas, at Austin, and then also he went on to become a Carnegie Fellow, and then he went on to become a professor at University of Michigan. Then he moved to NC State more recently. And today he's going to tell us a little bit about the origin of heavy elements and, you know, actual metals.
Yeah, we won't group them all together as Z. If you take nothing else away, maybe that'll be it. Thank you for this warm welcome. It's great to be here. I'm so thrilled to be in what's functioning as an astronomy department where I can talk astronomy with all of you for the day. It's really great to be here. I appreciate the invitation. It's great to be back in Texas again. Today I'd like to share a little bit about what I think is so exciting about this field right now. I'm trying to understand the origin of the heavy elements, and we'll talk about what that means. So I'll sort of introduce some of the big questions in the field today. I'll tell you about an old star we're learning some new fun things about that old star. We'll try to generalize that a little bit, so it's not just one star. We'll talk about some very heavy elements, fission fragments of very heavy elements, at least potentially. And I have time, I'll get into a little bit of dwarf galaxy, so local group archaeology, if we have time for that, and wrap up with sort of what I think is where this might be going and why I'm so excited about this, not just what we're doing now, but where we're going to be in 5, 10, 20 years in this field. So this is probably something you've seen, some version of this. This is a simulation of the collision of two neutron stars. This is meant to model a particular event that happened back. We observed it in 2017, not just as a merger of neutron stars that was detected in gravitational waves, but also in electromagnetic radiation for the first time. That was super exciting. I had nothing to do with that, but it was still great to witness that and to be present for that, to be living in a time when we could do that. The part of this simulation I want to zoom back into and focus on is the glow in the middle here, like that lumpy torus, the donut down there. That's called a kilonova. And that kilonova is likely powered by the electromagnetic radiation coming from that kilonova is likely powered by the freshly produced few hundredths of a solar mass of very heavy elements produced during that collision of neutron stars. And we got this view of this heavy element production for the very first time, where people were prepared and studied it. There were hundreds of observations taken in the weeks following this event to characterize it. And that was really exciting. When I talk about all of those heavy elements that were produced in that event, I'll roughly be talking about the bottom 2/3 of the periodic table. For me, that's what heavy means. I know everyone has a slightly different understanding of that. Roughly the bottom 2/3 of the periodic table, many of these elements you've probably never heard of before, and that's okay. I hadn't either until I did this. Most of those elements, most of the abundances of most of those elements are produced through something called neutron capture reactions. Now, if you want to grow a lighter nucleus into a heavier one, you probably can't do that with charged particle reactions. The Coulomb barriers, the repulsion is just too strong when you get to very heavy nuclei with all those protons in the nucleus. But neutrons don't see that Coulomb barrier. They go right into the nucleus, and you can grow your heavy nucleus that way. And then later beta decays will bring it back to something that's more stable. So many of these elements are produced through something called neutron capture reactions. One kind of nucleosynthesis, one kind of neutron capture reaction that I find interesting is something called the rapid neutron capture process, or the R process for short. The R process is the rapid addition of neutrons relative to beta decay timescales. It probably occurs in a relatively explosive environment because you need lots of free neutrons available to capture on all of those nuclei. Free neutrons don't survive very long out on their own, so you need to have recently freed them up from whatever was containing them, either nuclei or neutron stars. Probably an explosive environment that gives you a neutron density somewhere on the order of 10 to the 22 to 10 to the 28 neutrons per cubic centimeter. This R process probably produced most of the heavy elements in most of the oldest stars that we observe. And it also produced about half of the heavy elements that we find today in the sun and on the Earth. And those would have been produced in previous generations of stars, hung out in other generations or in the ISM for a long time, and then were incorporated into the sun and the solar system as it formed. So the diagram that's shown here shows a chart of the nuclides. So this is neutron number versus proton number. And all of those black dots there represent individual stable isotopes. Everything else in sort of the gray band there are nuclei that are either known or estimated to exist, but are radioactive. And we can use this diagram to watch an animation of the R process as it flows along, chart of the nuclides. So this is not for any particular site. This is just a general, what does the R process do? If you take some lighter nuclei, you bathe them in a soup of free neutrons for some period of time, what happens? Let's watch. You'll notice that the flow of nuclei in this R process event jumps up from light elements to heavy ones in only a fraction of a second. And then once that flow of neutrons shuts off, all of those heavy radioactive nuclei start to decay back toward the stable ones. So the R process occurs in an explosive environment that gives you the conditions where this can occur. Where is that environment? Well, we have some ideas. A kilonova, an emerging pair of neutron stars, is probably one. But trying to track down what all those ideas are is part of the one of the major goals outlined as part of the ASTR 2020 Decadal Survey. Thank you, Rob. This idea touches on all of these different, and everyone else too who contributed to that. I shouldn't. Everyone contributed if you were around, really. Touches on all of these different ideas, new messengers and new physics, right? That's the sort of the neutron star merger component of this, right? Tying gravitational waves and electromagnetic radiation together, worlds and suns in context. I'll explain in a minute why that link is here. Cosmic ecosystems, because we observe these R process elements in stars today, in our galaxy, in galaxies near our own. We can use them as tracers to understand how the galaxy was put together. All kinds of interesting stuff there. And once you understand something about the R process, this is the kind of thing you'd like to know. These are the questions you'd like to know, to sort of say, yeah, I kind of understand what's going on here. I understand my universe a little bit better than I did before. How were all these heavy elements, the bottom 2/3 of the periodic table, made? Which site or which sites were responsible for that? Can neutron star mergers do this alone? Do we need other kinds of rare kinds of supernovae maybe to contribute? Observations might be able to tell us something about that. And then what are the detailed physical conditions at all of those sites? This is the piece that ties back into the physics, not so much the astronomy side, but the physics side. What's happening at those sites? Can we get some information from those sites that we cannot get from laboratories here on Earth? And then once you understand those questions, you can use your understanding of the R process to inform your understanding of a lot of other interesting things, right? Stellar physics in the early universe, the hierarchical assembly of galaxies, such as our own Milky Way, the distribution of metals throughout the interstellar medium and the intergalactic medium, the heat budgets of planets. This is where we touched that third piece from the decadal. The heavy radioactive elements produce a substantial fraction of the heat budgets of planets like our Earth. So understanding where our process elements ended up does have an impact on understanding how those planets form and evolve. Do they have tectonic activity? What are their cores like? All those kinds of questions, magnetic fields. And then finally, can we use this to learn something about the nuclear physics, right? What's happening in the nuclei of atoms in ways that we either complement what we can do with experiments here on Earth or expand our reach of what those experiments can do. There's a lot of interesting stuff here you can do. So that's a lot of words. This is maybe like the one slide pictograph of how you can build some intuition about what all this does and how we do this. You can think of the abundances of the elements that you observe in the universe, the amounts that are there, as some product of the nuclear properties and the physical conditions. If you know any two of these, you can deduce the third. So if the nuclear data are known, and you can derive the abundances, for example, in a suitable star, you can learn something about the physical conditions at the site of nucleosynthesis. In an effort to inform our understanding, a few years ago, I was one of the co-founders of a group called the R Process Alliance. We are an interdisciplinary collaboration sort of between the astronomy and the nuclear physics communities of folks who are interested in solving the big questions related to the R process and probably raising some new ones in the process. As part of this work, we've already published several dozen papers at this point. Work is ongoing. It's a lot of fun. I enjoy working as part of this collaboration. And many of the projects you'll see highlighted here today were done as part of that R Process Alliance. Here's one example of something we did. This is a one-slide version of a high-resolution optical spectrum of one star. So wavelength versus flux. This is the star's name, it's a phone number, doesn't matter. But the important point to notice here is that every dip in that spectrum, every bump, every wiggle is real. Those are all the absorption lines in the spectrum of this star. And every one of those absorption lines carries information about, well, the piece that I'm interested in at least, the elements that are present, right? This is the chemical fingerprint once you disentangle it. You can zoom in on part of that, get a better view of what's going on here. This is, again, a spectrum, wavelength versus flux. What you'll notice in this panel is that all of the absorption lines of the very heavy elements, these are the ones that I've marked, that I've labeled with red. All of those lines, the absorption lines, are enhanced. They're deeper relative to in the black line, relative to the gray line. And that gray line is another star with an otherwise similar set of properties, stellar properties, temperature, metallicity, whatever. These are two stellar spectra. One has much stronger lines of the very heavy elements. And if you take that input data, so this is your observational material, you take that as one of your ingredients along with a model of the stellar atmosphere, a radiative transfer code, and the relevant atomic data for whatever atoms of interest you have. You put that together, you can derive the number density or the abundance, each one of these elements and more in that star. When you do that, this is the kind of result you might get. We'll look at a lot of figures like this today. You don't need to know the details, but atomic number versus log of the abundance. We'll see that pair of axes a lot today. All right, so the observational results, the observationally derived results, are the black dots here. Those are the abundances of each of these elements. The different lines that are shown there, the red and the blue lines, are comparison reference lines, I guess you could think of it that way. The red line is derived based on solar system material. So the R process contribution to the solar system, which you can kind of infer because you can actually go out and pick up meteorites, count the atoms in those meteorites with a moderate amount of physics that people were able to do more than 2 generations ago. You could infer what the S process contribution to the sun was. I'll talk about that in just a second. And once you know the total and the S process contribution, if you assume there's nothing else, you can back out what the R process is. It's just the difference in those two amounts of abundances. That's what the red line is. It's inferred. It's based on the integrated yield of many previous R process events that all enriched the sun before the sun was born. And we can talk about the comparison between the observational data and the solar system data. We'll do more of that in a few minutes. I still just kind of want to do some introductions to some of these ideas first. The R process is not the only way you can produce heavy elements. This is my one slide acknowledgement to that. I mostly work on R process elements, but there are other things that are interesting too. And the point of this slide, which again shows atomic number versus log of the abundance, each panel is a different star. So the observed abundance or the derived abundance pattern in different stars, showing you that, hey, these different patterns are pretty easy to distinguish if you have detected many elements. And the key to doing that is having the right observational data, I think. Anyway, many stars are sort of composite patterns of these different ones, but there are a handful that are relatively pure in the sense that that particular star was has heavy elements that were predominantly produced in one event or one kind of nucleosynthesis event. So there are other ways of producing heavy elements. Today we'll mainly focus on the R process because there's so much to say there. I think it's so interesting. You cannot reproduce the R process directly in the laboratory. Conditions are just too extreme. There were a number of tests that were conducted here on Earth to produce something like an R process. So the photo here shows an aerial view of a region called the Yucca Flats in the Nevada test site in the Western United States. This was built on Western Shoshone land. And over the middle of the last century, more than 1,000 nuclear devices were detonated here. And many of these craters you see are the results where things sort of fell in after the detonation. 23 of those tests were conducted with the particular goal of producing and studying the heaviest radioactive isotopes possible. But even then, this was still an imperfect reproduction of the R process, because the R process that occurs in stars probably occurs over longer timescales and at higher temperatures than were generated during these devices. So you get some information. It's potentially useful. I think they found that it was useful information in many cases, but it's still imperfect. And in any case, the testing program was ended in 1992. We can observe the R process in action. That's what that kilonova was most likely that we observed in 2017. So this is showing an artist's sketch next to real astronomical data here, photographs in the optical and X-ray of that transient that appeared in the outskirts of a galaxy about 40 megaparsecs away. It faded after a few weeks in most electromagnetic regimes. People continue to observe it for a long time, and there's information encoded in the shape of those light curves in different bands, and even in the spectra associated with that event. But even when you have a spectrum of that event, it's not always straightforward to interpret it in terms of what elements are present. That's sort of my games. I want to know what elements are present there. And this figure illustrates why that's so challenging. So this figure shows wavelength versus flux. These are 4 sets. Actually, it's one model spectrum. So this is a model. This is not real data, but it's model for 4.5 days after the event. And the different curves here represent different ejection velocities. And you'll notice that as you go from low to high ejection velocity, any potential absorption lines or emission lines that are present completely blur together. This is why this is difficult if you want to know the detailed element by element composition of what's coming out of that kilonode. There have been some extremely heroic efforts to identify just a few elements. Tellurium, selenium, or no, tellurium and strontium, I believe, have been identified. A recent paper presented some evidence for yttrium as well. So there may be a few elements that we can identify, but it's still pretty limited information. Here are some actual spectra of our process, of the kilonode that we associated with the R process, and you make the association just by comparing the colors, timescales, the expected opacities and model spectra for that radiation passing through billions of transitions of freshly produced, probably lanthanide elements dominate the opacity. So you can make some inferences, you can learn some things, but all that gold and all that platinum you kept hearing about in the press releases, news coverage, all inferred. It's not observed directly. There were so many of them, but we can observe gold directly in the spectra of our process enhanced stars. Old stars that hung out, were born near an R process event that occurred in the very early universe. To the best of my knowledge, there are currently about 6 detections of gold in stars, in old stars. Figures here show spectra around a gold line for 5 of them, and then the 6th one just didn't publish a figure. But you can do this for gold, platinum, and many other R process elements using the spectra of old stars. That's kind of the bread and butter of what I do. I have a lot of fun doing this, and I'm going to nerd out and show you some spectra for a minute. So please indulge me if you'll be so kind. These are spectra. Again, wavelength versus flux. Zoomed in around some R process elements produced by the R process in one particular star. That star is HD 222925. The different elements that are shown here are sort of listed at the top of each panel. You don't have to read them, it's okay. But the point to notice here is that, A, we can detect them right there. These are genuine absorption lines. When you have high resolution, high signal to noise, ultraviolet, that's the other key, spectra. The wavelengths here are in the ultraviolet part of the spectral range. You need to go above Earth's atmosphere to collect ultraviolet spectra, right? The only game in town for that is the Hubble Space Telescope, at least if you want high resolution spectroscopy. And these are all taken with STIS on the Hubble Space Telescope. But we can do this. We can do this. You can detect not just those elements, but in this particular star, this is the rich periodic table that emerges from just the optical and the ultraviolet spectrum. I really wish I could turn off that mute. Scroll over and do that. I don't seem to have the ability to do that. Okay. There are some words behind that little box. I apologize. Anyway, when you do this, you can really push the limits of what elements you can detect in any given star. This star, currently, we've detected 65 different elements in it. That is the best characterized in terms of chemical inventory, the best known chemical inventory for any object beyond the solar system. The key here is having access to the ultraviolet spectrum. UV gives you a 50% increase in the number of elements you can detect in old stars. Why is that important? Well, I've given you some reasons already. I want to introduce the idea sort of that underlies the entire subfield of galactic archaeology. The idea here is that stars are born, they live, they die. as they die, they produce metals, they return those metals into the interstellar medium where they're later reformed into later generations of stars. So as time passes, the overall metal content of the interstellar medium and the stars that are forming out of the interstellar medium increases. And as you go further and further in time, you get to a star like the sun that's been formed out of, I don't know, some large number of stars. I'm going to say on the order of 1,000. I don't know what that number is. It's not too, right? It's large. But you're looking at the average. You're looking at the time integrated, IMF integrated, just everything integrated yield of elements. Ideally, you'd love to go back to the second generation of stars that formed from the remnants of one previous event. Or at least a star that has whose set of elements, some subset of the elements was produced in one previous event. So that's what we do when we go back and look at these what we call metal poor stars, stars with relatively low abundances of metals. And we look for stars that have high enhancements of our process elements relative to the other metals. That's what this particular star was, HD 222925. You've seen this star before. I just showed you the spectra. It's so much fun. The Q is getting ultraviolet. Again, you're looking at log of the abundance versus atomic number. And once you have that abundance pattern, then you can start to do some physics. Then you can start to do some physics with it. So let's walk through a few things here. Some of the elements that I've highlighted in the yellow boxes are the ones that you almost never detect in little stars because you don't often have an ultraviolet spectrum because it's hard to get time on Hubble and you need to be observing relatively bright stars, right? For those of you in the know, you'll recognize this star's phone number is HD, not 222925. The key there is the HD. This is a catalog that was known more than 100 years ago. It's a bright star. This is the 9th magnitude star in V, right? That's kind of the scale you need to do if you're going to work with Hubble to get high resolution optical spectra. But those are the elements that you get when you do. That red line we talked about earlier was sort of the R process pattern that you would infer from the meteoritic composition of the solar system. Again, the time integrated average yield of many previous R process events before the formation of the sun. When you compare this old star and that red line to the sun, you find for the heavy elements, so like let's say 56 and beyond, there's a remarkably good match between those two. That's not a fit. That's a match, right? You can scale the overall amount up and down just to normalize, but the element to element ratios are spot on. That did not have to be true. When it was first discovered 30 years ago, it gave rise to all sorts of new interest in this field. That piece still seems to hold true today. But when you look at the lighter R process elements, so this is sort of in the like Z of 30 to 50 something range, they're different. The solar pattern does not match the pattern that we see in this old star. We have enough of the chemical inventory present finally in this star that we can really start to identify where those mismatches are. And it's not that one pattern is necessarily wrong. They're just different, right? You're looking at the time integrated yields of all these events in the sun. Whereas in this other star, HD 222925, you're looking at what one event produced in the early universe. So you may be getting some sense of the range, or the range of potential outcomes that could emerge from our process events over the course of cosmic history. There's a lot of physics there. What can we learn from this? Several big implications. Okay. This gives us a template that we should aim to match. Dirty little secret in the field is that every time someone has run an R process calculation for the past, I don't know, 2-3 decades, they've always had an eye on the answer, right? You kind of tune your model a little bit, at least some parameters, and then you allow others to float. You tune your model to reproduce the solar R process pattern. We don't have to do that anymore. We still can, but you don't have to because we now have reasonably complete templates, element by element templates of the R process, what the R process can produce from other stars. So that's a big thing in itself, just that sort of philosophical, intellectual advance. We can do something different we couldn't do before. This particular study, published last year, made some comparisons of different neutron-star merger model nucleosynthesis predictions, compared them with the observed abundance pattern or derived abundance pattern in this star, and found that, there's a really interesting thing that happens that because the lead author here, Erica Holmbeck, comes from sort of a nuclear physics background. And they're all about trying to constrain the nuclear physics models, which mass model or which set of models for whatever nuclear property you're interested in are the best at reproducing results for isotopes far from stability, where you're having to extrapolate the way your model works based on where you can calibrate it. That's scary. But when you do that, if you simply choose a different set of input nuclear physics, you get differences. I know it's a little bit small to see here. You get differences in the predictions that emerge from your model that are of the same scale as the differences between the model and the observations, or different conditions that you put into your model. And the fact that for the same set of conditions, you get different outputs depending on different nuclear physics tells us we need to constrain our nuclear physics a little bit better. So you can use this as a guide to help inform which nuclear experiments are likely to give you the best bang for your buck, which ones you should run first at the new big accelerator lab, for example. We'll talk about that briefly at the end. So that's one outcome of this, is that you can now start to motivate those experiments a little bit differently than you did before. There's so many elements here, you can start to use this pattern to guide your interpretation of the other abundance patterns that are present. We've spent the last 30 years deriving abundance patterns of the R process in other stars. This is not the first time this has been done, right? But we're doing it in a different way now, by adding that ultraviolet component. And I don't know, let's take one particular thing here. For example, let's use this new relatively complete pattern to inform our understanding of what contributions, if any, transuranic fission, for example, might have. What is that? Elements heavier than uranium are called transuranic elements. They exist, they're all radioactive, mostly have relatively short half-lives. Those are the elements that are sort of highlighted in the orange boxes here on the periodic table. There's uranium. We go beyond it here, beyond it here. What among those elements can nature produce? That's one question. There's all kinds of questions around this, but they're all radioactive. They're all transuranic nuclei. And when they decay through that radioactivity, the major decay mode for many of them is a process called fission, where the nucleus simply splits. And the process of fission gives you two lighter neutron-rich nuclei, a handful of free neutrons, and energy in the form of gamma rays. And then those two lighter nuclei go back and they populate the middle of the periodic table. So you've taken a very heavy nucleus from the bottom and you've created two back toward the middle somewhere. Fission has been studied in the nuclear physics community for a long time, and there are still a lot of open questions around that. For example, what distribution of elements can be produced during an R process? How heavy can that R process go? How heavy can nature go? Can you get out to this sort of like proposed island of stability, way up the nuclear chart, somewhere up here? Can you get up to that island of stability somewhere? Super heavy elements, maybe. All of the nuclear mass models that underlie this for the heaviest elements are extrapolations. How reliable are those extrapolations? We'd love to know. And then not just producing those elements, but the fission process itself. What is the distribution of the fragments that come out of those fissions, right? When the nucleus splits, what actually emerges? These are questions that we'd love to be able to try to answer. Just a little bit more background here before we try this with astronomy. On the experimental side, on the left-hand side here, these are figures. Don't worry about the details. This is atomic number versus it's a distribution. It's probability distribution. And the key point to notice there is that there's sort of two peaks, a lighter peak and a heavier peak. Those are measured or experimental for individual isotopes. So you take an isotope, uranium-236, for example, let it fission in a laboratory, and then just count what comes out of that experiment. So the right-hand side panels here are all theory. So the different curves are different, some parameters different in the calculations of the fission process itself. And the key point to notice is that the theory and the experiment both agree on sort of this two-peak distribution, right? It's bimodal. Not exactly sure exactly how bimodal, but they're sort of kind of two peaks separated by some amount. There's a critical need for experimental data here, and we haven't been able to yet get this from the nuclear lab. Can we use stars to provide some information here? I will argue that answer is yes. And in the process of doing that, I need to walk you through how. So we'll look at some graphs in just a minute that show on this axis, the elemental abundance ratio that we'll use as a proxy for the overall strength of that R process. Broken into iron. On the vertical axis will be the log of the abundance ratio of various pairs of elements produced by the R process. So they're one element to another. If there is a flat trend in this diagram, or no trend, if there's a flat result here, when you plot many different stars on this diagram, then that might tell us that the two elements shown on the vertical axis are being produced in similar amounts every time, regardless of how strong the R process is. If there is a positive non-zero slope that is statistically meaningful in some way, that tells you that one element might be produced more than the other as the strength of the R process increases. Here's one way to visualize those results. I've divided the different results into 5 panels, sorted by increasing atomic number. Some of them get covered up here. Light, lighter, light, moving to heavy in that sequence. The elements in panels A, C, and D exhibit no significant positive slopes, so just sort of flat lines. And that would indicate to me that those elements are being produced in relatively similar proportions, regardless of the strength of the R process. The elements in panel B and D show that positive slope. And that tells me that one of those elements listed here might be being produced more than sort of their neighbors, the reference element, their zirconium or barium, as the strength of the R process increases. So one way to interpret this is the proposal is that the elements in panels B and E could be representing sort of those peaks of the fission fragment distribution. So as the R process gets stronger, you throw more and more material toward the very heavy end because maybe you have more neutrons or it's over a longer period of time. I don't know, something like that perhaps. You produce more transuranic elements, they fission back and produce elements in sort of region B, that's ruthenium, rhodium, palladium, and silver, elements 44 through 47, or the heavier peak, or there could be elements out here, gadolinium, dysprosium, elements 64, 66, and beyond, other elements that just naturally require stronger R process for their production anyway. So that's one way you could interpret this. I don't know of any other process that would give you sort of this same signature. If we find something else, that's great. Right now, I'm going to use this interpretation for lack of a better idea. But if that's true, let's think about some of the implications. One, I think this would indicate that our process events were capable of producing transuranic elements, at least the ones that occurred early in the universe, enriched the metal poor stars that we're observing these elements and this signature in today. Maybe that was a relatively common behavior. Next, you can infer the mass of those heavy transuranic nuclei by adding up the mass numbers of the fragments. If you do that, you find that masses with nuclear numbers greater than about, A values greater than about 260 would have been required. And that 260 is interesting because it is heavier than any of the nuclei that were isolated in the debris of the nuclear weapons tests that were conducted in the last century. I think the heaviest one that has been publicly acknowledged there is 257, and we're going to at least 260, perhaps beyond, with the stars, if this signature is what we're claiming it is. Another implication is that I think that this could boost the prospects for actually detecting transuranic elements directly in the kilonova aftermath of neutron star mergers, things that are happening today. At least we're observing them today. So the graph here shows time versus magnitude. So these are kilonova light curves for the mid-infrared bands on Spitzer and JWST. On the timescales of months after an event. The bottom set of curves show the predicted light curves without fission from californium-254, an isotope that might be produced and has a relatively long half-life, and curves with californium-254. And you'll notice that there's a big difference in the brightness of those two sets of curves, and that could be observed with JWST on a timescale of months after an event, if one is found in the next few years. That would be very exciting. And that would sort of confirm this picture that we're seeing, that our process events perhaps can indeed produce transuranic elements. All right, in the interest of time, I am going to jump ahead and look toward the future. One of the things that's so exciting about this feature is a laboratory called the Facility for Rare Isotope Beams, FRIB. This was a partnership between state of Michigan, SF, and DOE, I think. I hate to give credit where it's not due, but I think that's what it is. Oh yeah, here we go. Okay. Anyway, it's an operation. It was built. It turned online in 2022. This is a real facility now. This figure shows predictions for what FRIB could do for this particular science case. So what you're looking at here in the graph is atomic number versus number of isotopes of that number. So if you go across the rows in the chart of the nuclides, the bottom histogram here shows the number of known isotopes. So isotopes that have been produced and studied in a laboratory previously. The green curve, the next one, shows you the number of isotopes that are estimated to be capable of being produced and studied at FRIB. And then the top one shows you the number of nuclei estimated to exist. FRIB gets you to most of those nuclei for the first time. And that gives you huge leverage, understand and constrain the R process experimentally here on Earth. So that's one exciting thing. On the astronomical side of things, there's a couple of new instruments that either have come online or are soon coming online that are going to allow us in the public community to do this, not behind university proprietary paywalls. Stellies at SOAR and GHOST at Gemini South. GHOST is in operations. The data are beautiful. So these are going to be fantastic sources of new observational data to do this kind of science in the decades ahead with public facilities. Beyond that, the next big things, literally, are the extremely large telescopes. The ASTRO 2020 Decadal recommended the US community invest in both GMT and TMT. We'll see where that lands. These telescopes would give us access to many more stars, fainter stars, some of the ideal stars we'd like to do that are just a little bit beyond our reach right now with sort of the 6 to 10 meter class telescopes. That would be a fun thing to do, or to do this in dwarf galaxies, again, that are still a little bit too far away. Galaxies around the Milky Way. I've been involved with the European version of this, the European Extremely Large Telescope. Andes is the high resolution optical NIR spectrograph for the ELT. It's second generation instrument for the ELT. It does all kinds of stuff, right? Biosignatures, all the same things that GMT and TMT want to do more or less. The science case documents for this instrument are out. I led one of those on stars and stellar populations. This will be fantastic to watch what happens with this. Starting in the 2030s and beyond, this should be a real workhorse instrument to do all kinds of interesting science. The other big thing I'm excited about is Habitable Worlds Observatory. This might emerge before I retire. But the goal here is to build something the scale of JWST, but sort of have Hubble-like capabilities. The piece of this that I am so interested in is the ultraviolet spectroscopy, continuing that legacy that Hubble has helped to establish. And no matter what your science is, if you have an interest in doing this kind of anything that you can imagine doing with Hubble today, but on a much bigger scale and deeper, farther, whatever, fainter. If you want to do that in 2040s, efforts are underway now to define sort of the science cases for habitable worlds. I'm involved with one of these, again, sort of the ultraviolet spectroscopy piece for stars and stellar populations. But all science areas are working to do this right now to sort of start down that path of getting the instrumental designs so the technology, the appropriate technology can be matured and designed in the 2030s, launched in the 2040s. That's the two-sentence version of that. This is going to be really exciting if this comes to fruition. And this is the next thing for that ultraviolet piece that I've been talking about so much today. Future, we always conclude, is bright. I look forward to a day when we have all kinds of abundances for all of these different elements and many more stars, many more templates. I look forward to the day when EFRIB has started to fill in some of those missing pieces of the chart of the nuclides with actual experimental data that give us better constraints on our extrapolations. And then we can learn something about the physics of how our universe works and the origin of the elements all around us. Thank you for your time.
Go back to your plot of like everything versus European. And you were looking for like flat or not flat, basically.
This one.
Yeah, so you group the elements based upon Z there, and it seemed somewhat kind of random to me who doesn't know anything about that part of the table. Like why did you do that grouping the way you did? Yeah, first of all, are these halo stars?
These are primarily halo stars. They're all metal poor at some level.
Right. Is there like any rhyme or reason why like you chose how to?
Indeed, there is. I'm glad you asked. Thank you. So what I didn't show you here is that we made the same plots, but one element at a time.
Okay.
So instead of grouping them together, antherium plus pranctodium and iridium and samarium, we did each of those elements individually for about 40 stars. And if that element showed a trend, we grouped it with other elements that showed trends.
Oh,
Without doing any magic, just what fell out of the analysis. The elements that showed trends were all neighbors here or neighbors here. And so they got grouped together, and then the other ones got grouped together.
like a nuclear physics way to understand that, or
The nuclear physics way I'm proposing to understand that is that this set of elements represents nuclear masses that are enhanced by the lighter fission fragment peak, by throwing a lot of our process material beyond uranium and letting it fission back and enhance the amount of elements that's there.
Actually, this is the exact slide I wanted. So you normalize by iron essentially, right? And so is there any like dependencies that come with that, right? Like does it change if you change the element you're finding your ratio with?
So the x-axis.
Yeah.
That's what your question is about.
Yes.
We tried other elements there. We tried other expressions. So instead of normalizing by iron, I was a little bit uncomfortable with, and the nuclear physicists were really uncomfortable with. We tried normalizing by hydrogen. Right. And you actually get a weaker effect for some reason. I think what might be happening, this is hypothesis, but we're trying to get enough data to actually do something with this in the next 5 to 10 years. I think what's happening here is that the iron is telling you something about the environments where those R process enhanced halo stars are born. The piece of the talk that I skipped over in the interest of time talked about making correlations between R process abundances and environment through dwarf galaxies and stars that are today we would just simply call halo stars because they're orbiting the center of the Milky Way, but may have been born in dwarf galaxies, not unlike some of the surviving ultra faint dwarf galaxies.
Cool.
For your conditions of where this might occur, you had mentioned like kilonova and that you were looking for other possibilities too. Are tidal disruption events one of your possibilities on your list? No.
Tidal disruption events, I don't think have been proposed because you still need something. Let me make sure I understand what tidal disruption meant. TDE means to you.
Okay.
Does it mean a normal star running through fission or sorry, running through fusion in its core or shells, or does it mean tidal disruption of a neutron star?
I'm not a star person, so you can pick your favorite star. But I'm just thinking a star being destroyed by, say, a black hole.
Okay. So you need a source of neutrons. That really is the key. If you're disrupting a neutron star, that's a source of neutrons. If you're disrupting a main sequence star, probably not a source of neutrons. So, I mean, I think understanding is that most TDEs are sort of main sequence stars or at least evolved stars of some kind. Someone in the audience may want to sort of jump in here if I'm, put me back on the tracks if I've gone too far off. But I think that's why they've not been proposed. The other sites tend to be sort of rare classes of supernovae, massive star supernovae, things that are rotating rapidly, maybe high magnetic fields with jets, where you can kind of funnel a lot of the neutron-rich material away from that proto-neutron star before all the neutrinos come out and bring the neutron to proton ratio back to sort of closer to 1-to-1, but you want to keep it really neutron-rich. So you need some way to funnel those neutrons away, and that's one way that's been proposed to do that. That might be a very viable way, just that maybe doesn't happen all that often. I don't know. But that's sort of the other kind of scenario we envision.
So the gravitational wave GW17 event, so that is one of the best kilonova event, I guess. So are you expecting more such events in the next observing months? And if so, how is it going to improve?
Yeah, how are we expecting more events like GW17, 0817 in the next gravitational wave observing runs? And if so, what happens? What do we do then? That one, I don't know, we got so lucky with that one. It's 40 megaparsecs away. That's close, right? Most of these things are the other kind of neutron star mergers that may or may not have electromagnetic counterparts detected with them much farther away. Like that's where you expect them to be happening, right? That wouldn't happen in our backyard. I hope we get lucky again with another one. I don't know. I mean, I'm not as deeply involved in that kind of work to sort of know what the predictions are for like the spatial distribution or I mean, you expect one of these things. I think like if you base your neutron star merger rate on that one event and all the other non-detections, you get like, I don't know, 1 per cubic gigaparsec per years or something. I forget what the denominator is there. It's not high. And I mean the overall rate of neutron star mergers relative to massive star supernovae, for example, in the 3, 10 to the 4, something like that. So it's a low rate to begin with. If one happens, my understanding is people are ready, right? People are always sending in target of opportunity proposals to Hubble, JWST, and probably multiple big optical telescopes. And I'm sure there's all sorts of small telescope networks that have been set up in the last decade as well that are just waiting for they're doing other exciting stuff in the meantime, but I'm sure could turn on a dime, do this kind of stuff. And if it happens while the sun is not in that general direction, I think we'll be ready. I hope we can.
Anyone else questions for Ian?
Anything online?
No. Right, well, we can thank Ian again.